Hi, welcome back to the final lecture on Bayesian approximation and mechanism design. We're going to continue talking about posted pricing, but looking at the situation where uh, we cannot, as the mechanism designer, enforce the order that the agents arrive and consider their prices. Will allow the agents to arrive in any order, and this is called oblivious pricing. And what we're going to be doing is showing that, like before, oblivious pricing is approximately optimal. Before we showed in E over E minus 1 approximation when we can put the agents in order, that's about 1.58, and we're going to show a worse approximation bound for oblivious pricing. Our approach is going to be make a connection between pricing and profit inequalities, which come from uh, uh, an area of optimal stopping theory. And we're going to be connecting this theory of profit inequalities with the theory of virtual values from auction theory. Okay, we're going to be looking at the following stopping problem. An online gambler faces n games. Game I has a prize distributed according to a distribution capital Fi that is known. The gambler plays each game in order, and when playing game I, realizes prize Vi drawn from distribution Fi, either takes this realized prize and quits, or returns the prize and continues playing. And so the gambler faces a stopping problem. They have to determine which prize they want to keep and stop with. Right. And so if you are thinking about how you would optimally solve this question, this problem, the answer is straightforward. You would employ backwards induction. Okay, on the very last day, obviously you should take the prize. This is your last chance at getting a prize. Okay, that gives you some expected value, the expected value of Fn the last day, the last game. Okay, on the second to last day, you should take the prize and quit if its value is at least the expected value you could get on the last day, the expected value of Fn. Okay, and on the third to last day, you should take the prize if it's at least the expected value you would get from the last 2 days. And so you can continue by backwards induction to solve for at what price, at what threshold you would use on each day. Okay, of course, naturally, the thresholds you use on each day are going to be different on each day. And as you might imagine, the revenue, the payoff you get is sort of increasing as you walk backwards in time. So these are going to be decreasing thresholds that you would play by backwards induction. Great. So that's complicated. And as we like to do when we're considering approximation, we're going to look for simpler approaches. So I'm going to define a threshold strategy as fixing a single number, v hat, where the gambler takes the first prize, which has value at least v hat. So unlike the backwards induction solution, which has different thresholds for each prize, this is a single threshold. Okay, I want to note that there is an implicit tie-breaking rule happening here. Okay, in other words, what happens if multiple prizes are above the threshold? Which prize do you take? Well, the implicit tie-breaking rule is you take the first one. Great. So here is the theorem. There exists a threshold strategy where the expected value of the gambler's prize from playing this threshold strategy is at least half of the expected value of the maximum prize, sort of in hindsight. If we knew what all the prizes were going to be, this is just the expected maximum of the prizes. Okay. So this theorem is called the profit inequality because, in some sense, the gambler is getting close to uh, the performance of the prophet who could see the future. Okay, there are two extra notes about this theorem. One note is that one such threshold is the threshold where the probability that the gambler gets no prize at the end of the day. In other words, we play a single threshold and all of the prizes are below the threshold. So the gambler gets no prize. Even on the last day, they say no. Choosing the threshold so that the probability this happens is exactly 1/2 is one such threshold you could choose. And the second note is that this result holds and is invariant of the tie-breaking rule. In other words, if we chose a different tie-breaking rule, like, for example, if there are multiple prizes at the threshold, maybe the gambler gets the prize with the lowest value, or maybe they get the prize with the highest value, or maybe some other tie-breaking rule. It doesn't matter what the tie-breaking rule is. The theorem still holds. So the tie-breaking rule is a detail. Great. So I'm gonna give you the proof of this theorem. I've just restated it here from the previous page. Great. Okay, so we're going to prove this theorem. And I've got 3 parts. Okay, so I'm first going to fix an arbitrary threshold, and then I'm going to start doing some analysis. Okay, the first part of analysis is getting an upper bound on the profit. Ref. I'm then going to get a lower bound on APX, the gambler's performance. And then I'm going to plug in a value x equals 1/2, which is the probability of no prize, and combine the upper and lower bound. Okay, great. So we're going to fix a threshold. And just to get some notation, let's let qi be the probability that the value is above the threshold. So probably the gambler would take this prize if. Okay. And so I'm going to define x to be the probability the gambler gets no prize, and that is the product of 1 minus qi. So 1 minus qi is the probability that the prize is below the threshold, and so the product of that is the probability that all of the prices are below the threshold. Great. So x is the probability of no prize. All right, I'm now going to look and get an upper bound on the gambler, the expected maximum prize. Okay, so the first thing I'm going to do is do nothing. Okay, so the expected maximum prize is equal to the following. So I add v hat, and I subtract v hat from inside the max. Okay, so here I've just added and subtracted v hat everywhere. So that was nothing. That's the expected maximum price. Okay, now I'm going to get an inequality by only taking this value max of vi minus vi hat when it's non-negative. Okay, so I'm going to define this notation. Okay, this notation means the max of vi minus vi hat and 0. Okay, and great, so these variables are all non-negative now. And so since I have the expected maximum of some non-negative variables, I can replace that with the expected sum of non-negative variables and get an even, bigger upper bound. Okay, so my analysis thus far is concluded that for any threshold vi hat, I can upper bound the profits prize, the expected maximum prize, by the threshold plus the amount by which the maximum prize exceeds the threshold. In fact, sorry, it's the threshold plus the amount by which all of the prizes, any of the prizes exceed the threshold. Great. Now I'm going to get a lower bound on the gambler's performance. Okay, and so to get a lower bound on the gambler's performance, the gambler gets a prize. So remember, x is the probability of no prize. So 1 minus x is the probability of a prize. And if they get a prize, well, the threshold was vi hat, so the value of that prize must have been bigger than vi hat. Okay? And so they're definitely going to get that. But then they're going to get some more. So I want to figure out what more they get. How much more they get than just the v hat. Okay? So I want to add up the contribution of the prize when it's more than v hat. Okay, but this is going to be hard to analyze when there's more than one prize above the threshold. So I'm going to only look at this additional amount I get when there's exactly one prize above the threshold. Okay, so we're going to sum over all prizes the expected amount that prize is above the threshold, conditioned on all other prizes, j not equal to I hat, being below the threshold, and then times the probability that we're in this event that all other prizes are below the threshold. Okay, and now to analyze this a little bit, this probability that all other prizes below the threshold, this is just the product of j not equal to I of they're below the threshold. So that's going to be 1 minus qi. Okay. Great. And this product, 1 minus qi, that's going to be bigger than or equal to x, because that just compared to x has an additional 1 minus qj, 1 minus qi multiplied by it. Okay, so that's bigger than x. That's my first observation. And my second observation is if you look at this conditional expectation, note that the random variable here is vi, and the conditioning is on all other vj. And so this conditioning is independent of the random variable. Okay, therefore I can just drop the conditioning entirely. Okay, so I'm going to drop the conditioning. And what I'm left with is this inequality. It's a lower bound on the algorithm's. This is a lower bound on the algorithm's performance. Okay. Now, if my distribution f is continuous, then I can select v hat so that X, the probability of no prize, is exactly 1/2. Okay, and notice if we select an X such that the probability of no prize is exactly 1/2, and we plug in our upper bound and our lower bound, then we see that the upper bound is exactly twice the lower bound. Okay, so again, we're going to look at this upper bound, we're going to look at this lower bound with X equals 1/2. Okay, and so in particular, this is going to be 1/2, and this is going to be 1/2. And we see we get exactly 1/2 times the upper bound. Okay, and so that's our result. Okay, as an exercise, I suppose that this distribution is not continuous, which means I might not be able to find an x, a v hat, where x is exactly 1/2. I claim there's another way to select uh, v hat. So find another way to select v hat to also get a theorem where the gambler is getting half of the expected maximum prize. That's exercise 4. Great. I now want to connect this this gambler's problem to Oblivious pricing. So I want to find prices that are good for any arrival order of the agents. And the idea is to apply profit inequalities to virtual values. Great. So I'm going to define, again, so the profit inequalities can get as a single threshold applied to all prizes. So we're going to apply profit inequalities to virtual values, we're going to look at a single virtual value to use as a threshold. Okay, so I'm going to define a uniform virtual pricing to be a set of prices. Okay, so prices in value space, so v hat, such that the virtual values corresponding to two different agents at those prices are equal. This should be v hats. Okay, so that's a uniform virtual pricing. All right. And now I claim that uniform virtual pricing is a 2 approximation. Okay. Excellent. And the proof is this is just a profit inequality on virtual values. Okay, so what is ref? It's the expected maximum price, which is the expected maximum virtual value. Okay, and what is our approximation mechanism? It's going to be posting a uniform virtual price. Okay, and uh, so we're analyzing our revenue now from posting a uniform virtual price, but we know that revenue is equal to virtual surplus. Okay, and so asking what is the virtual surplus of posting a uniform virtual price? Well, that's just the virtual surplus according to the profit inequality. Okay, and here I'm taking advantage of the fact that the profit inequality was invariant to the tie-breaking rule, because when I post these prices and the agents can arrive in any order, the worst thing that would happen for me is, if some subset of agents wanted to buy, the worst thing that would happen for me is the agent with the smallest price bought. Okay, so we're going to do tie breaking by smallest price in the profit inequality. And to guarantee that that when we uh, uh, allocate in this fashion, uh, we're guaranteed the result that the the approximation, the expected virtual surplus from posting prices b hat is at least the expected maximum virtual value. Great. Okay, and so this wraps up this series of mini lectures on Bayesian approximation. So going back over what we've talked about, we talked about the philosophy of approximation, how approximation can be used to identify details or salient features, how they can identify robust mechanisms, uh, uh, and such. I promised you I'd tell you why collusion was a detail, and that's because these posted pricing mechanisms are oblivious, are impervious to collusion. The prices are fixed, the agents can't collude to get different prices, and so they're sort of naturally collusion resistant. So collusion's a detail. And I gave a brief review of auction theory, quantile-space, revenue curves. I showed you that random prices uh, are nearly as good as optimal prices. I talked about a general approach for approximation, showing that for proving that mechanisms are good approximations, which is looking at this ex-ante relaxation. And we saw two methods for proving that pricing is good. We saw the correlation gap method for showing that sequential pricing is good. We saw the profit inequality for showing that oblivious pricing is good. Uh, and you can find further reading and further approximation bounds in chapters 4 and 5 of my textbook manuscript, Mechanism Design and Approximation. Uh, thanks a lot for your attention to these videos, and